friends, Mrs. McBride here. Hopefully you had a good time playing around with the electric field hockey lab yesterday. Again, sorry that I am not in class today. I am still in New York City for one more day. What we're doing today is we're looking at page 6 on the notes, and you're definitely going to need your calculator for today as you're doing this. Okay, so what you did yesterday is hopefully you took a look at what the electric field looks like around a charged particle. And we're just going to take some notes on what those look like. Okay, so if we had a positive charge here, okay, what I want you to be able to say is that the electric field around a positive particle is going to radiate out like this. And the reason why is because we're always pretending we put a little positive test charge here. Okay, so if we put a positive test charge here, it would be repelled from the positive here. Okay, I always think about how to remember that the arrows go out is that positive people radiate out. Okay, whereas negative people keep it all in. Okay, so if we put a little positive test charge here, it would be attracted to the negative. So what we find is for a negative charge, all of the arrows are going in. Now, the more arrows you have, the more charged it is. So when I draw mine, I always draw them with 8 arrows. If they had 16 arrows, you might say to yourself, wow, that is twice as charged, okay? Or if they only had 4 arrows, you might say, oh, that is half as charged, right? So the more arrows, the more charge. Things start to get interesting when you put 2 things together. Okay, so for example, if you have a positive and a negative that are close to each other, what you find is, again, positive people radiate out, negative people keep it all in, okay? But what happens is like this one was starting to go out, but then it's like, hey, I'm kind of attracted to you. Same thing here. This was gonna start to go out straight, and then I was like, nope, I'm kind of attracted to you. So what we see is we get a little bit of bending here. Okay, now why is this important, or when would you see this? Well, I could give you something like this on a test and ask you questions about it. Okay, and you would need to know, look, the positives have the arrows going out, the negatives have the arrows going in. Okay, so let's keep going. Let's say, for example, we have a positive and a positive. Okay, well, we know that these are like charges, so they are going to repel each other. So what we find is that as this is going out, it sort of curves up, repelling each other. I always think these kind of look like spiders because there's lots of different legs here. Okay, and what's weird about this one is that there's a space right in the middle here that has no electric field. The electric field, I don't know why I drew that like that. The electric field is equal to 0 right in this spot right here. Okay, there's no electric field. There's nothing happening right in this spot right there. Okay, and then the negative and the negative are very similar, except the arrows are going in the opposite direction, right? So again, negative people keep it all in. We're drawing more spiders. Okay, and again, no electric field right there in the center, no electric field. Okay, and last but not least, if we had 2 charged plates, okay, so this is like 2 pieces of metal that are really close to each other. Let's say one has a positive charge and one has a negative charge. You might be saying to yourself, why on earth would we have this? Well, we would have this because this is what a capacitor is. We're going to talk more about a capacitor later. Okay? And we would see that the arrows would point down like this. Okay? Now, what's the hardest question that I could possibly ask you on a test? Well, let's say I had something that looks like this. I said, here's A and here's B. Okay, you don't have to draw this. My question to you is, what is the charge of A? Hopefully you're saying positive because the arrows are going away. What is the charge on B? Hopefully you're saying negative because the arrows are going in. Which is got more charge, A or B? Hopefully you said A because A has more arrows. Okay, that's as hard as it gets. All right, let's do some math here. All right, this sample problem says a 4 times 10 to the negative 7 kilogram styrofoam bead has 600 excess electrons on its surface. What is the magnitude and direction of the electric field that will suspend the bead in midair? Okay, well here we are, suspending in midair again. We talked about this the last time we were doing notes, okay? If we're suspending in midair, that means that the forces must be balanced, okay? So, what forces do we have here? Well, we always have gravity pulling us down, okay? And then we must have some sort of electric force pulling up, okay? So I'm gonna go and grab my handy dandy pink sheet and I'm gonna say, all right, well, which equation should I use here to find the electric force? This one or that one? Hopefully you're saying this one right here is when we're talking about two different charges. We only have one charge. So let's not worry about this one because we only have one charge. Let's go down here where we only have one charge. So if E is equal to Fe over Q, I can multiply both sides by Q to get out of the denominator, or I can get that EQ is equal to Fe, okay? Or I'm going to say that in this case, Fe must equal Fg, or EQ, my electric field times the charge, must equal mg. Okay, so we're looking for what is the electric field, so that's our E. Okay, now we need to find the charge. Okay, well, do we have the charge? Well, kind of. We have 600 excess electrons. So what do I do with that? Well, I know the charge on one electron, and I have 600 of them. So I'm gonna say, okay, if I take 600 and I multiply by the charge on one electron, 1.6 e to the negative 19. I should probably make this negative too. I can set this equal to m, 4e to the negative 7, times my little g, 10. Okay, so what I'm going to do is I'm going to multiply. I'm going to get out of scientific mode here. I'm going to multiply 4e to the negative 7 times 10. And then I'm going to divide by parentheses. 600 times negative 1.6 e to the negative 19. End parentheses. Okay, and I'm getting that the electric field is equal to negative 4.17 e to the 10 newtons per coulomb. Did you get that too? Hopefully. That's pretty big. That's a pretty strong electric field. Okay, one more. Now this problem is a doozy, so hopefully you brought your math hat and you are ready to go. This problem is as tough as it's gonna get, and there's gonna be one just like this on the homework, which will be something that you should totally do right after this. Okay, this one says, a charged ball of mass 0.1 kilograms and charge -6 microcoulombs. Oh, geez Louise. Microcoulombs. Okay, micro, I will tell you, is -6 e to the -6 coulombs. Is suspended between two metal plates with an electric field of 300 newtons per coulomb. What angle does the ball hang, and what is the tension in the string? Okay, well, let's take a look at what forces are acting. Hopefully you're saying to yourself, well, we've got gravity. And the tough part about this is that we've got tension here at an angle, and there also must be something that's pulling this in this direction. This is our electric force that's pulling this over. okay? And we have one force that is acting not at an angle, or not straight, it's acting at an angle. Okay, so we have to break this force into its components. Okay, if this is my angle, right here, this is the side that is opposite that, or I'm going to have T sine theta, because sine always goes with opposite, right? Sine is the opposite over hypotenuse. And if this is my angle here, this side is the adjacent side, and adjacent always goes with cosine. Okay, so if we're suspended here, what I really can do is I can say there are two sets of forces that are equal, right? Because the two up forces, T cosine theta and FG, must equal the two sideways, right? Those must equal, and then the two sideways forces must equal each other too. Okay, so we're gonna have two sets of equations. Equation number one is gonna be that FG is equal to T cosine of theta. Equation number two, T sine theta equals FE, okay? Now we're looking for the angle and the tension, okay? So, what do we do? Well, let's see if we can plug in some stuff here, okay? We can start by saying that FG is mg, and we know that FE is equal to EQ. Okay? This isn't really helping us. We've got tension and tension. Okay? I need to solve this algebraically. So what I'm going to do is I'm going to divide both sides by cosine of theta. Or I'm going to get that mg over cosine of theta is equal to t. Now, some of you might be thinking, Mrs. McBride, how does that help you? Okay, well, I'm going to do a little math here. I'm going to bring this over here. This is going to give me mg over cosine theta times sine theta equals EQ. Okay? Well, those of you who brought your math hat, what is sine divided by cosine? I'm hoping you are all just screaming into the computer, tangent, that sine over cosine is tangent. Okay, let's keep going here. We've got the mass, 0.01. We've got little g, 10. Tan theta we don't have. What is E? I'm running out of room here. 3,000. And Q? -6 e to the -6. Okay. I'm going to take what is 0.01 times 10. Okay, so this side becomes 0.1 tangent of theta. And this side is 3,000 times -6 e to the -6. -0.018. I'm going to divide by 0.1. Tan theta equals -0.18. And I'm going to take the inverse tangent of -0. I'm going to take the inverse tangent of -0.18, and this is going to give me theta. So I take the inverse tangent of -0.18. Okay, and I'm going to get that my angle in this case is -10.2 degrees. That was a lot. Okay, the good news is that now that this is done, the second part's super easy. Okay, because now we can bring this information over here, and we need to find what is the tension in the string. Okay, so we take our mass, 0.01, our little g, which is 10, and we multiply, or we divide by the cosine of -10.2. Okay, and I get that the tension in the string is 0.10 newtons. Okay, that's tough. That's certainly as tough as it's going to get. But hopefully you can use this to work on that homework question that looks very similar to that. All right, thanks friends. Bye.